In this section, we'll now start talking about the naming conventions and some of the properties of the complete stationary states of the hydrogen atom, that is, the radial and the angular parts together. We derived in previous videos that the energy of the hydrogen atom can be written as this E sub n, where n is what is called the principal quantum number, and it goes as minus 1 over n squared. And we have that all of the eigenfunctions take three different quantum numbers. So there's the n, which is the principal quantum number, L, which is the angular quantum number, and m sub L, which is the magnetic quantum number. And the eigenstates, or the eigenfunctions, can be written in this form here. We have a radial function that depends on n and L, and then the spherical harmonic of L and m sub L. And putting all this together, we have that the principal quantum number can go from 1 to infinity, L must go from 0 to n minus 1, and m sub L can go from minus L up to plus L. And now what I've written down here below are the first few full complete eigenstates, meaning including the radial and the angular parts, for the n equals 1 and the n equals 2 principal quantum numbers. And from looking at these, we can see the two different components, right? So the eigenstates that we were working with have a radial component, which is here. And in the examples, the radial components are the exponentials, or all the parts that depend on r. So it's the exponentials, and then the polynomials that are sort of stuck or sitting next to them. And then the second component are the spherical harmonics. And so this is where all the angular part is. And the angular parts are only really show themselves for the n equals 2 and L equals 1 states, which I'm highlighting those parts here. And notice this last line here. This is the eigenfunction corresponding to n equals 2, L equals 1, and then m sub L equal plus or minus 1. So this equation here is really two different solutions, and they only really differ by this plus or minus I right here. So you either have e to the plus I or e to the minus I phi. So now we can start talking about a few important properties or a few important results that come out of this analysis. So first thing we can do is try to count up the number of states for each n level. Okay, so for n equals 1, we know that's the only possible value for L then, because L has to be less than n minus 1. The only possible value for L is 0. And because there is only one possible L equals 0 solution for the spherical harmonics, this leads to just one possible eigenstate with n equals 1. For n equals 2 now we have two possibilities. So we either have that L is equal to 0, and this gives us one state, or these two combined we have that L can also be equal to 1. And because this is now showing, this is one state here, and this is two states, we know that there are 2L plus 1, or three possible states for the L equals 1 spherical harmonic. And so that means that in total, we have 4 states, or 4 possible eigenstates at the n equals 2 energy level. All right, if we follow this through for n equals 3, for n equals 3, we know we can have L equal to 0, which gives us 1, or we can have L equals to 1, which gives us an extra 3, or we can have L equals to 2, which gives us 2L plus 1 with L equals 2, gives us 5 new states. So we add all of these together, and then this tells us that there are 9 possible eigenfunctions that all give the same energy for n equals to 3. So if we line these up, right, so we have for n equals 1, we get 1. For n equals 2, we get 4. For n equals 3, we get 9. This is looking like a pretty obvious pattern, and so we can deduce the degeneracy for the quantum level, for the quantum number n is equal to n squared. So what this means is that for a given energy, E sub n, there are n squared different eigenfunctions that all give the same energy. N squared distinct orthogonal eigenfunctions that all give the same En energy level. Now, because there's just so many of these, we need a simplified way to be able to talk about them. So we're going to introduce the notation that is really commonly used to talk about atomic orbitals, which will be written as n, and then there's normally a symbol that corresponds to the angular momentum, and then there's optionally some further symbol that corresponds to the particular m sub L value. And so I'll give you some examples. So you might be used to thinking about the 1s orbitals, right? So this follows this pattern where you have, so n equals 1, and then s signifies the angular momentum value, and then there's only one s function, and so there's no subscript here. And a similar example would be like the 3p orbitals. Okay, so there are, when you talk about the 3p orbitals, these correspond to n equals 3, L equals 1. And then if you're talking about them in collectively, you'll maybe omit any sort of subscript, but otherwise you'll often add, 3px, for instance. So where do this s and p come from? So this particular mapping, or the identification of particular L values to a letter, is basically a historical convention that is still really commonly used today. And it goes a bit like this. So for L equals 0, this is called the S state. And the historical names come from assigning particular peaks in the sodium absorption spectrum. So for the L equals 0 or the S state, this is a shorthand for the sharp. For L equals 1, we have P, and this is due to principal. For L equals 2, these are called D for diffuse. For L equals 3, these are called F states for fundamental. And for everything past 3, we just start going alphabetically. So starting at L equals 4, then everything after this we go FG, and there is no real name for G, this just happens to start going alphabetical finally. Again, these names are just historical names that were used to describe a particular sodium spectrum. They don't necessarily mean too much about the eigenstates themselves, but they have carried over into the definitions of these states. And so we can rewrite these states over here using this naming convention. And so what we have up top is the psi 1s, and then we have the psi 2s, psi 2p. In this case, it would be 2p0. This is psi 2p plus and minus 1. Okay, so this is the naming convention for the total hydrogen atom stationary states. Starting in the next section, we'll start discussing actual plots for what these things look like. And from there, we can learn some of their properties and also start talking about things like radial distribution. So we can ask questions like, what's the average distance away from the nucleus for particular states?